Welcome to this SE23 OpenMP booth talk about OpenMP and performance. My name is Ruud van der Pas and I work in the Oracle Linux engineering organization. Within that organization, I'm deeply involved with the GNU application profiling tool called gprof-G. It's in the open source and it's actually great fun to work on that. But today I want to talk about OpenMP and performance. And my claim is that you can get good performance with OpenMP and your code will scale, but you have to do things in the right way. And the whole purpose of this talk is to give you some idea what I mean with the right way. It's going to be very basic. I want to go back to the basic and basically give you a checklist of things you can check for your own code and see whether you can make some improvements. So my claim is here is if you follow the guidelines, the performance should be decent. And an OpenMP compiler and the runtime should do the right thing. You may not get blazing scalability to high thread count, but it definitely gets you started on the track to improve performance. And in any case, should you ever go to the OpenMP performance court, the lawyers there have no case against you because you did everything according to the book. I really like OpenMP because it's so easy to use, and that's great. I can very quickly do a what-if analysis. It's easy and quick to implement some idea and see whether you're on the right track. That's all great, but there's a thing that you need to know, and that some constructs are more expensive than others. For example, few people realize that a parallel region is expensive. It does a lot of things for you, but that'll take time, that'll take resources. So parallel regions are expensive, so you don't want to have too many of those if you can avoid it. And that's the part of OpenMP that hasn't been documented very well, and in this talk I hope to address some of that. Another thing is that whenever you write dumb code, you probably get dumb performance, and we can leave out a probably you will get dumb performance. And the reason is that OpenMP is very prescriptive. You tell the compiler, here's a parallel region, parallelize it. It will do so for you. But what if that parallel region only contributes to the total time with 1%? It doesn't matter for the performance. But as you do that, it may become very inefficient because there's a cost of parallel computing. So you parallelize something that doesn't contribute and you add overhead to it. Well, that's not a good idea. So that's what I mean with you gotta do that with care. And the way to do that is through a profiling tool that will guide you. So the first step to take, and this is the high-level tuning strategy, don't forget about that. Start with the most efficient algorithm. In terms of complexity, an algorithm of complexity n to the power of 3 is going to take more time than one of n squared. That's just the way it is. So you start with the most efficient algorithm that you can find, and then you start parallelizing it. Unfortunately, in the literature, there are cases where people took a very inefficient algorithm, but it parallelized so nicely. Well, that's not what you want to do. You want to start with the best one and then make the best out of it. And with that, a profiling tool that tells you where the time is spent is absolutely necessary. I don't care what you take, of course. There are many available. Just pick one. But use that tool to tell you where to focus on. Then in the application, find the highest level of parallelism, but there still should be enough work to do. What do I mean with that? Well, let's say you have a 3D problem and you can parallelize across the 3 dimensions. That's nice, but it won't give you a more than 3x speed up no matter how many threads you use. That's kind of not nice. So go lower in the application, find a fairly high level. Higher is better in that sense, but so that you can use many threads so you can take advantage of the hardware you have access to. Then use OpenMP and you do that in an efficient way. You're going to use OpenMP in a smart way. Whenever you do tuning, whether that's sequential or parallelization, you always have to be prepared to do some performance experiments. You may have that brilliant idea, you try it, and then it turns out to be slower or no benefit. Happens to me quite a lot. I could fill a whole talk with how to make codes go slower. You're probably not interested in that, but don't be discouraged. Keep on trying, and eventually you will find out what's going on and you crack it. And again, in that, a profiling tool can help you too. Before I continue, there are two things that I want to talk about. They're related to performance, and I find that a lot of misconceptions in it, so I want to cover that. The first one is about cores and hardware threads. Cores are the computational engines in your system. Even laptops have multiple cores these days, and they do all the crunching for you. And as an acceleration technique, that core could support multiple hardware threads. That's part of the design. Some have it, some don't. These hardware threads are acceleration engines. They accelerate the execution of a single application or a whole workload. The hardware doesn't know, doesn't care, but it's an acceleration. And the whole idea behind hardware threads is, and it's a really good idea, is that whenever the core, or technically said the pipeline, is not doing anything, why waste those cycles burning energy and wasting time? Instead, you can do something else, like get another thread or application in and do some work. And that's illustrated in this diagram. In this diagram, I'm showing what would happen if I run two applications and I don't have any hardware threads. So the first, the light blue application starts executing, and then there's a gap. I could be waiting for I/O, could be cache misses or whatever. And when its time slice is up, the dark blue application goes in, and it may or may not have gaps as well. But that means there's a lot of precious time and energy wasted. Instead, if I had two hardware threads, what I could do, then fill that gap with some other work. Like while the light blue application is waiting for I/O, the dark blue could start executing and use that hardware in a more meaningful way. And in that way, I save time. And the reason I mention this is that there are two kind of levels of speed up. Depending on the application, you may or may not benefit from hardware threads. If there are no gaps, then there's no gain in using additional threads per core. And that's where the misunderstanding comes in. People say, well, I have 16 threads in my box. I don't see much speed up beyond 8 or 9. Well, yeah, that's because there are no gaps. And if there are no gaps, you don't get any gain. So that's why I want to mention those the hardware threads. And in the case study at the end, I'll have an example of that. Another big one, a really big one, is Amdahl's law. And I want to show that by ways of an example. Let's say your application needs 100 seconds to run, and 80% of that runtime can be parallelized. So that means 80 seconds out of the 100 can be executed in parallel. So when I use 4 threads, that means 80 over 4 is the time for that parallel part, and 20 seconds left because I didn't parallelize that. So the total time comes out to be 40 seconds. That means the total speed up of the program is 2.5x, which is really great, but it's not 4. And that's where the confusion comes in. People parallelize the application, they throw a number of threads at it, and they're disappointed they don't see 4x on 4 threads or 8x on 8 threads. Well, most cases it's Amdahl's law. And Amdahl's law says the part that you didn't parallelize, those 20 seconds that were left, are going to get you rather sooner than later. And you can make a chart of that. And I've done that for a system with 16 threads. And here's the observation. I'm looking at the parallel speedup as a function of how much of the runtime has been parallelized. The red line, the horizontal line, is a sanity check. If I don't parallelize anything, I'll never get a speedup, no matter how many threads I use. The dark green is on the opposite side of the spectrum. Perfect parallelization, 100% parallelization. So I get a perfect linear speedup, 16 times on 16 threads. Great. But look at the curves in between. For example, if I have parallelized half of my runtime, I won't get more than 2x speedup, no matter how many threads I throw at it. If I have 95% parallelization, I still won't get more than 10x. That's kind of a bit depressing, but it's the way it is. But always look at the bright side of life. What we see here is that it's not so hard to get an initial speed up on a low number of threads. And that's exactly what we see in practice. It's not that difficult to get a speed up on 2 threads, 3 or 4. But as this curve shows, as you start increasing the number of threads, it gets harder and harder to get a speed up. Or a meaningful speed up, I should say. And again, remember 95% means 10x. Yeah, that means there's a challenge to parallelize as much as you can and sort of defeat, and you can't defeat a law, but try to minimize the impact of Amdahl's law. There's another reason that I am bringing this up. What Amdahl's law says is that the part that you didn't parallelize, the serial or single thread part, will get you sooner than later. So you can't be lazy in that sense, and the first gain you can get is pay attention to single thread performance. You want that serial part to be as short as possible. So before you start parallelizing your code, you're going to play with options to get the best sequential single thread performance out of the box. And then you're going to parallelize. That's your first savings. So now we covered that. I want to give some tips and tricks how to avoid writing inefficient OpenMP code. First of all, and maybe that's already clear by now, don't parallelize what doesn't matter. You only run the risk that a small part is slower because of the parallelization. That's not what we want to do. So again, use the profiling tool. That will tell you where the most of the time is spent, and that's the part you're going to parallelize. Another big one, a really big one, don't share data unless you have to. Sharing data is really absolutely wonderful. I use it all the time, but you use it with care. Sharing read-only data like a big table is absolutely no problem. The problem may start when you start modifying shared data, especially on large systems with NUMA effects and all those kind of nasty things. The big message is only share data when you have to, when you really have to do that, and minimize the use of shared data. Use private data as much as you can. Another one is minimize the number of parallel regions. In other words, maximize the work you do inside a parallel region, because each parallel region is expensive, so you want to have as little as possible of those. And an example is the parallel 4. Parallel 4 is syntactic sugar for a parallel region with just one for or do loop in it. When you have one, that's fine, but when you have more back to back, that's going to be evil, and that's what this slide is elaborating on. So I have a single parallel 4, no problem at all. There's a for loop or do loop in Fortran there, no problem at all. But what if this is the structure of my code? I have n loops, and each one has been parallelized with a for loop, parallel for loop. A parallel 4 is a full parallel region, so I got all the overhead n times, and I also can't use the no wait clause, and I have to elaborate a little bit on that. In parallel computing, you need a barrier. A barrier means that all threads wait in the barrier until the last one arrives. In that way, you know some work has completed before you continue, and you absolutely need that in certain cases. That's why OpenMP has implied barriers on certain constructs, including on a work sharing for loop, but not on the parallel region, because for good reasons you need a barrier at the end of the parallel region. So this means that this block of code has n barriers. Now a barrier is expensive, especially as you increase the number of threads. Barriers don't scale very well, especially on larger systems. So you want to minimize the number of barriers. Well, here you have n and you can't get rid of them. Now look at this. This is one parallel region, and inside I have n individual OMP 4s, not parallel 4s, because that would give nested parallelism, which is a performance disaster. Just the OMP 4 for each of those loops. And now I have one parallel region, so I reduce the overhead significantly. And I can use this no wait clause. The no wait clause will leave out the implied barrier, so I can do barrier level optimization, which is always a good thing. It will help your scalability, it will help your performance. One you can always leave, one barrier you can always leave out is the last one, just before the end of the parallel region, because that 4 already has an implied barrier. So now I have one at the end of the parallel region and at the end of the 4, so I have 2 back to back. And while the second one is admittedly faster, it's still a waste of performance. So you can safely add the no wait. Do compilers do that? Well, the last time I checked, I don't think they do. And this is where you can help and just add that no wait clause. So that's enough about barriers. They are important. You need them for correctness, but they do matter for performance. The same is true for locks and critical regions. Look into atomic constructs in OpenMP. OpenMP has quite a set of atomic constructs. They're more fine-grained. They take advantage of hardware instructions. Critical regions and locks, they're very heavy, and they give you scalability bottlenecks. Atomic constructs are way faster, way more fine-grained. So look into that and only use a critical region when you absolutely have to, and see if you can replace it by an atomic construct. At the end of the day, everything matters. And think about Amdahl's law. All those things you don't parallelize, they will get you. They're part of the sequential performance of your code. So fix everything as you implement your parallelism. Here's another example. All these things are taken from real codes, and this is one that I found in an application. There's a single region. Well, single region is really useful to do some work that only needs to be done by one thread. That's great. But the single region has an implied barrier. And here's a second one. Well, why would you? That's overkill, and that's a really bad idea. So just leave out that second barrier. That will be my solution. And that will, again, save two back-to-back barriers, which is not good. It will cost you performance. So very simple change, and I don't think compilers are ready to do that for you. So think about that no-wait clause. Simple but very powerful. Be aware that you are allowed to use it, that you don't introduce a data race, of course. Another one of my favorites is the schedule clause. If threads do a different amount of work because of an irregular problem size, or maybe you're working on a triangular matrix, the schedule clause can give a more dynamic workload distribution and can greatly help to avoid load balancing issues. Nested parallelism, don't use it. Don't use it. It's evil from performance point of view. Consider tasking. And even with the schedule clause, you can look into the task loop as well. So there are other ways of doing things, and they're more efficient from a performance point of view. I want to finish with a case study because I want to illustrate some of the things that I've said, how that works out in practice. And I picked an example from graph analysis. I am going to be brief and quick because I don't have time to go into all the details, but I want to give you a feeling. So this is the starting point. I ran this application on a cloud instance that was using 8 cores. Each Skylake core has 2 threads. So in total, I have 16 OpenMP threads to play with. And what I'm showing you, the bar chart, is the time of the search in this algorithm. That's what this graph algorithm was doing. It was doing a search. And what you see as I add threads, the time goes down. That's great. So I do see a benefit even beyond 8. This system has 8 cores. So I do see a benefit in reduction in the time as I start using those second threads in the core. So that's really great. The dotted line is the parallel speedup. And the blue one is the ideal speedup. The dark one, the black one, is the measured speedup. And we see a huge difference. What we see on 16 threads, the total parallel speedup is only 3.2. And that's a bit disappointing, actually. So the question is, can we do better? And yes, I used a profiling extensively that showed to me there were quite several inefficiencies in this application, like redundant barriers, for example. So I cleaned up the code in a way. I made it more efficient by applying some of the things that I talked about before. And what we see, that's the bar chart, is the green one is for the second version. And we see that although on 1 and 2 threads I don't see much of an improvement, actually no improvement at all, at 4 and beyond the algorithm is faster and faster and faster. And at the end of the day, on 16 threads, I have a 2x performance improvement. And the parallel speedup increased from 3.2 to 6.5. So that's a nice saving. It wasn't all that much work, and I shaved off these inefficiencies. Now the question is, are we done? That's the hardest question to answer in parallel computing, in performance tuning in general. You don't know whether there's anything left on the table. So you typically do some more experiments, and that's what I did. So I was using the profiling tool to look at the what's called the timeline. The timeline, time is from left to right here, and these horizontal bars, there are 2 types. The green one is the operating system state. Green means the operating system is in what's called user mode. It's happy, it's just running your application. Anything in this tool, any other color than that green is bad news, but this is good news. So the operating system is happy with our application. And the second horizontal line is the single thread performance, what we're seeing. Then we see the performance for 2 threads. And that looks good because the first thing we see, without even digging into anything, is the initial phase of this algorithm is faster, and the whole search part is faster as well, search and verification. So we definitely see a speed up. Well, that's good news. But then I zoomed in and I started looking at that second thread, and what you see is there are gaps in the execution. The main thread is crunching along quite nicely. It's just doing that search and the verification. But the second thread has gaps. That's not good. It means we're not making optimal use of our resources. And the profiling tool told me this is where you spend most of your time. So let's see whether we understand where those gaps come from. What we see is a very large OMP4 spanning the whole block of code here. It has a fixed length outer loop running from K1 to something called old K2 minus 1. So that's a fixed length. But within that, we have a second loop. And that second loop has an irregular length. It depends on the index values that it gets from the outer loop. So potentially different values of K have a different length of the second loop. And then we see a nested if statement. And depending on whether those ifs are true or false, you could end up doing a lot more work. So there's what we call irregular control flow. Depends on whether those ifs are true or not. And that means there's an irregular workload per K iteration. For different values of K, threads do different amounts of work, and that's called a workload imbalance. And as soon as that word is dropped, then you should think about the schedule clause. And that's what I did. I switched to dynamic scheduling. I used that scheduling clause. And I just show you the final result here. What we see, that's the blue bar chart, is the performance, the search time for this version with the dynamic clause added. And we see that on the single thread, there's actually a 1% slowdown. That's not a surprise, because dynamic is more expensive than the default static scheduling, so we see a little bit of slowdown. But immediately after, we see the performance drop and drop and drop, and ultimately, the final version of on 16 threads, I get 3x speed up compared to the original. So it was 2x, it now dropped to 3x. The speed up is 9.5 instead of 3.2. And another interesting thing is that on 8 threads, I get a near linear speed up. That goes back to those hardware threads. On 8 cores, I have 8 threads. And then when I start adding the second thread, I still see a benefit. It's not that much, but why waste it? You have the hardware anyhow. So that just shows you a little bit of how you approach these things. You identify bottlenecks, you fix them, and progressively you get better and better performance. So as takeaways, I see many applications that benefit from improvements in the performance. There's a lot of low-hanging fruit. Just look at the checklist that I gave you, and I think you'll be on the right track to improve the performance. There are always exceptions, of course, but in general, these are general things to fix. Use that profiling tool and don't guess. For the computer, it could be something very different that's time-consuming than what you think based on your physics or chemistry. So thank you for your time. I hope you found this useful. Whenever somebody comes to you and says OpenMP does not scale, please correct that person and say, bad, OpenMP doesn't scale. So good luck with your tuning, and again, thank you for your time. Before I really go, I wanted to point out 2 websites. One of them is openmp.org. That's your one-stop place for anything about OpenMP. You will find the specifications there. You will find reference guides, the announcement of events, and there's a forum where you can ask your question or see what others have been posting. And the second one is specific to SE23. That's where all the booth talk videos and presentations can be found, so you can view them and watch them whenever you're ready for it.